to the sides, to the columns, into the ground. And here you see the deflection of this. And this is exaggerated, so I multiplied the true movement so we can actually see something here with our eyes. As expected, see the slab in the middle, they come down a bit. Even here in the tower, it deflects, also at the staircases. And then overall, this would be the dead load, super dead load case. If we do a wind load, for example, we say, let's push from the left onto that building, I'm loading the vertical surfaces, in this case the columns, and I'm also loading the tower top here, the church. And on the leeward side, again, there is turbulence, and there's also wind load that is kind of sucking on the building to push it to the right further. You can see now here that the deflection looks obviously different than it was from the super dead load, where the load was coming down. In this case, especially the slender tower, which maybe isn't braced sufficiently yet, moves quite a bit. And you would, while here you would limit the slab deflections, in this case it's more the interstory drift or the kind of sideway deflection, the racking, that may become problematic. Imagine again you have a facade here, something sensitive to deflections, that could crack and lose its watertightness. A third one would be temperature. We call that delta T. Here I'm assuming a hot summer day in the entire church. Think about it like wants to blow to the outside, it wants to expand. So all these things are trying to move and grow because temperature wants to make things larger. Because something here, the church is restricting these sides. You see, it's not fully symmetrical in this case, but it would be for an expansion. In any case, most of the members are going to the outside where they were before. If I had the winter case, think about everything shrinking, everything contracting. Of course, it cannot contract where it's fixed to the ground because the support points with the foundations aren't really allowed to move. It's just an example of these different load cases and the deflections, the serviceability limit state. If I now look at frequencies or possible failures, look at this one here. This would be the staircase swinging. And it could vibrate to the bottom, to the top, and it would go up and down. But I checked it in this case, this frequency was in the range of 5 Hertz for this particular span and cross-section that I chose. So even though the model shows me what would happen, this is probably just big enough to not worry about the staircase being in vibration when people use it going up and down. Another mode is this church tower mode that would swing to the side. We saw before, this is not a static deflection, but you saw before it was somewhat weak. And so this one would be something we would have to investigate a bit more. Also the tip acceleration, there was a bell in there. And higher modes are basically less critical, but you see this more or less is like a cantilever that deflects like this. And this one is like a system which has an intermediate support here. And you can see that it's hard to draw. It's probably better drawn like this. It's like a second S mode. But the idea is the same. You have to check it for frequencies. So this would be the serviceability limit state for deflections. These pink lines make sure the maximums here are okay, or in this case it will be even more to the side, and you investigate it. And this one would be the serviceability limit state in terms of vibrations of the staircase or even tip accelerations of a tall tower top. To go to the right here now. I prepared this. We're almost through with the first lecture. This is now the ultimate limit state. Now, wherever a certain color, in this case red means you're overstressed, becomes red, that tells you that in these corners maybe the moments and the forces are higher than what the steel or the concrete or the wood can take. So if something is red, you have to go back and make the member stronger, like choose a bigger profile, for example. Where the members are not red, you're okay. So I purposely made this a little bit too thin so you could see that usually in corners or mid-span it hurts us most. And then the engineer goes back and tells you what the depth of these members is required so that all the red goes away. This was maybe a load case where we were looking at mainly dead load, super dead load, and some snow. Maybe this one is maybe one load case where we were looking at wind from the side. What I'm saying here, each picture corresponds to a different combination of loads, so we want to check them all. Or up here, it's probably if you just load the tower top with the wind. And all the pictures combined would probably show quite a bit of red here, but if you optimize and choose the right sections, at the end everything is within stress capacity, within material capacity, and the utilization is smaller than 100%. That's here the target always. And then stability, the last mode we described as something to be examined in every system. I have a friend here going online. And that is buckling. See, where do you think if you have a load up here, the load goes most of it? See, some of that load probably travels to the left, that's correct. But a lot of the load here travels to this middle column. Its area of influence, yeah, is kind of like in this zone. And again, some of that load travels down here, and here it's probably less. So you can see that that first column buckling, this person here, this buckles out. Because of continuity, there's like corresponding lines, what all the adjacent members do, but you can see here is the mode that is really happening. And if we look at the stresses, even before we had 100% red stress utilization. So had we not done the stability check, we may have had a problem and the church collapses even though the stresses were fine. What are other modes? See, other modes, it depends on if I now maybe just load the snow load up here. Other modes usually, again, in this case is sort of another global mode with corresponding side modes. But the entire thing could have also been swaying to the side, or here something happens. I think this is the driver where this column fails. Or say we have a big wind load again, possibly this entire thing, as we started to talk earlier, may have gone to the side. This could also happen from earthquake, for example. And so the stability analysis is trying to find possible buckling risk or global sway or twist. And then I'd have to go and, again, make this column here stronger so that it doesn't buckle out. Or maybe I even want to put in another bracing so that my system buckling length is reduced. But that's something often that's in conflict with the architecture that doesn't want a column or a bracing there in the middle of the room. And so, in summary, if we say something like the snow load is acting on a building, on the roof here,